I welcome you all to the second track about deep vision. My name is Nathanael Ratner, and I'm the CTO of the computer vision at Rafael. I think it's not a coincidence that the three works that we're about to see are somehow related to security and defense applications, but obviously the techniques that will be presented are widely applicable to a range of applications. I remind everyone to silence their cell phones, and without further ado, I invite the first speaker, Dr. Michal Holtzman Gazit. Dr. Gazit graduated from the Technion and completed her postdoctoral work in the University of British Columbia in Canada. She's currently with Rafael Research, doing computer vision research, mainly deep learning methods and generative adversarial networks.
Okay, hi everybody. So today I'm going to talk about state transfer using generative adversarial networks and what we do with them in the real world rather than just fool around with images. So as you well know, deep learning, end-to-end learning is involved in many of the tasks that are around us today. Whether we're talking about natural language processing, such as translation, computer vision, image captioning, object detection, and many, many more. Voice applications, such as voice-to-text, and even in robotics. It's all around us. Specifically for computer vision tasks, such as image segmentation, object tracking, object detection, localization, image registration, classification, and many, many others, they all require a large amount of data. So today, as you well know, there are many open databases for various tasks, such as ImageNet or MS-COCO, for classification and detection, and there are semantic segmentation databases for autonomous driving. But sometimes we don't have the database that we require, and we need to collect it. We need to collect a large amount of images. And that is a tedious task, and also it's very expensive. So we need to collect the images, and we also need to label them according to the task. And sometimes we can't really do that. In our applications, we can't always collect those databases, so we need to synthesize them. So consider the case that we have no real images, or maybe just a few, but definitely not enough for a database. And we can synthesize images. We can use synthetic images or images from a different domain. And those synthesized images try to simulate the relevant image domain. And if we have an automatic tool that we can generate synthesized images, then we actually have sort of solved the problem. We can generate a big labeled database for the relevant task, and then we can train our computer vision task, our deep learning network, on this set of images. So we sort of solved the problem. However, since I'm standing here speaking, we didn't really solve the problem. The simulated images are not similar enough to the real images, and they don't represent the true statistics of the real domain. And therefore, when we train an algorithm on that simulated database, it's bound to succeed less in a real scenario when we deploy the algorithm. So we need to solve the gap between those simulated images and the real-world scenario. So the solution to this is to better mimic the style of the real domain. And this way, we can actually allow better training and then better deployment of the computer vision task. So how can we do that? So we're going to do it using generative adversarial networks. As some of you know, or most of you know, generative adversarial networks is a vastly growing field in the field of artificial intelligence. It was first introduced in 2014 by Ian Goodfellow from Google. What it does, it's two separate networks that compete against each other. So on the one hand, we have a generator that is trained to generate samples that fool the discriminator. And on the other hand, we have a discriminator, some sort of detective that trains to distinguish between the real images and the fake images, the fake samples that are produced by the generator. And this is a minimax game, and it alternates between the generator and the discriminator. So they are trained together up to a certain point. And as you saw before, this graph is the number of papers written about guns since 2014, and especially in 2017. This is an exponentially growing field. So it looks like this is the way to the future. And one of these, so if we want to be more specific, just to remind you how it works, if we have a grayscale image and we want to produce color images from grayscale images. So we have a generator that receives the grayscale image, and it's some sort of encoder-decoder, and it tries to color the image. On the other end, we have a discriminator, another network, that gets the generated color images and some real images. And it tries to label the images according to their origin. It wants to label the generated images as fake and the real images as real, while the generator tries to tell the discriminator actually that the generated images are real. So it wants to fool the discriminator. It wants the discriminator to label the generated images falsely. So this is the equation that it's trying to minimize on one hand and maximize on the other hand. So the generator tries to minimize the equation while the discriminator tries to maximize the equation. So this is the basic GAN, and as I said, there are many papers regarding GANs. One of them, as you saw in the first lecture, is a cyclic GAN. So how does this work was shown in ICCV 17 by a group from Berkeley, and it works in the following way. So it has, for instance, if we want to turn zebra images into horses, seems like they really like zebras and horses in Berkeley, and if you want to change zebra images into horses, you train a generator to transfer the style from zebra images to horses, and then there is a discriminator that receives the real horses and fake horses and tries to determine their true label. In addition, there is a second generator that receives horses images and tries to turn them into zebras, another encoder-decoder. And then there is another discriminator that receives zebra images, real and fake, and tries to determine if their label. And in the end, there is also a cyclic loss between the original zebra image and the final zebra image after encoding, decoding, and then encoding, decoding again. So this works both ways. The mapping is learned both from zebras to horses and from horses to zebras. And this cyclic loss enforces structure. So this GAN actually can work in an unpaired manner. That is, it's completely unsupervised. We have a set of zebra images and a set of horse images, and then they don't have to be of the same location, and obviously it's not the same zebra or horse. It's not the same scenario, and this cyclic loss maintains the structure. So the final objective of this cyclic GAN is the original GAN objective, from X to Y, from horses to zebras, and the GAN objective from zebras to horses, okay? So this is, again, the minimax game between the generator and the discriminator. And in addition, there is a condition, another constraint, that is the cyclic loss, okay? So it's per pixel loss on the original image, between the original image and the reconstructed image in the end, and this is both for zebras and horses. So while this is a very nice idea, and it really works nicely for horses and zebras, and also face to ramen and other really neat applications, we needed it to work in the real world for us. So we have some more constraints that we need to apply on this objective. The first one is similarity to the original image. We don't want the image to change the structure too much, since we only want to change the style. We also want to make the result valuable to the task, and I'll talk about that soon. And finally, we need to balance the power between the generator and the discriminator. Okay, so first one is the similarity loss. As I said before, the generative adversarial network, this cycle GAN is unpaired. And since we only want the style transfer, we want to preserve the image shape. So we want to enforce similarity to some extent between the input image and the generated image, and we add an L1 loss, per pixel loss, between the input image and the generated image. Of course, we add this loss with some weighing factor. We don't want to impose too much of the original structure on the final image, but still we want the horse to remain a horse and not change it into a dog, for instance. The second loss we added to this objective is a task loss. We want to ensure that the output is valuable to the required task. For instance, if we're talking about classification, if we want to change, if we have a face image and we want to change the orientation of the face, if it's looking at a different direction, we still want it to be the same face. We don't want the face to change into a different person. So we added a constraint on the image class, if we're talking about the task that is classification, and we want the label of the image to remain the same before and after the generation. Okay, so if I have an object, if I have a dog, I want it to remain a dog. If I have a cat, I want it to remain a cat. Finally, there is a problem that the discriminator always wins. This GAN network is a very fragile thing, and it looks like there is some point that it can arrive at the Nash equilibrium. There is a zero-sum game, and we want the competition to be equal forces. So if the discriminator always wins, always knows that the generated image is a fake one, then this doesn't work well enough. And there are many papers today that talk about this. There are many roads to equilibrium. And we tried a few regularization schemes, and the one that worked best for us was WGAN LP, which this is its equation. And what it does, it penalizes the gradient norm of the when the discriminator is larger than 1. So this was originally used for regularization of Wasserstein GANs, but actually it works also in the general case of GANs. And this helped a lot to balance the power between the generator and the discriminator, and allowed us to get much better results from our generative network. So let's look at some results. So if we're looking at those synthetic images we're talking about in the beginning, and we want to make them look more real, And in the bottom, you see, here are some trucks, synthesized trucks, and on the bottom you see real trucks, okay, this one and this one. We see that they look a lot different than the synthesized image. But after training the system long enough, we get the style transfer that we actually wanted. And these trucks look a lot more like real images rather than just synthesized ones. And the last image is the reconstructed image at the end of the style transfer, and you can actually see that it manages to recover the original truck pretty well. In addition to color images, we also tried this on infrared images. So these are completely different images that demonstrate the heat, actually, of the subject. And here you see a real infrared image. Well, this is a simulated infrared image. And after training this generative network long enough, we managed to actually get images that look much more like real infrared images with the heat in the engine and some halo around the truck, things that we couldn't really see on the we couldn't really get the synthesized image to look like them. And in addition, when we used those images for training our computer vision task, we managed to get an improvement in our results. So we managed to get a few more, we managed to get higher success rate in our result when training the computer vision task. So to sum it up, we used the cycle GAN, and in addition, we added some constraints such as similarity loss, task loss, and regularization to help balance between the generator and the discriminator. And that's it. Thank you.
Thank you very much. Questions, anyone? Yes.
Sure.
So I'll just
so you're
repeat the
talking about
question.
this slide? Okay, so the leftmost image in those three is the synthetic image. In the bottom, we have a real image of a truck, but we do not have many of those, okay? And this is the image after the style transfer, after the generator from synthetic to real domain. This last one on the right end is the image after the style transfer from real domain, or sort of real domain, to the synthetic domain. No, what we're interested in is the middle result, okay? The final result just helps us see that the reconstruction worked well. We're interested in this middle result. This is what we're gonna use to generate our database.
Okay, any other questions? Okay, let's thank the speaker.